first one, we have the same ball. It's released from rest on two different slides. And we want to know which one is the ball going to be moving fastest at the very end. So right here versus right here. We're going to not derive an equation, and friction is negligible, which means energy is conserved. So let's think about the one that is moving fastest at the end is the one that has the most kinetic energy at the end. Now where that kinetic energy comes from is in the loss of potential energy. In part A, I'm losing all of this potential, whereas in part B, I'm only losing some of that potential energy. So that means that A is going to lose the most potential, which means it will gain the most kinetic since energy is conserved. So slide A loses the most potential energy, has the greater height change, so will gain most kinetic because energy is conserved, right? Implied, but energy conserved. So because it loses all of that potential, it's going to gain all of that kinetic, and the one that has the most kinetic is going to be faster at the end. So slide A. You also could say, so some people are doing that here, this is all kinetic energy, and this is some kinetic and some potential. You can do this, it's going to take more effort, right, more writing at least. So here, they both start with the same total amount of energy. A converts to all kinetic at the end, B is some kinetic and some potential at the end, meaning if they have the same total energy, this will have less kinetic overall. What will not work if you just say A is all kinetic at the end, B is some potential and some kinetic, so it must be slower. That is not enough. You have to talk about they have the same total, this is all kinetic, whereas this shares between it. It's easier to just do like the change. Alright, derive an equation for the velocity of the ball on A and on B. So A is all potential, goes to all kinetic. M cancels, multiply by 2, take the square root. B is all potential, goes to some potential and some kinetic. Subtract over. So this is what I'm saying, the kinetic at the end is not all of it, right? Only some of it transferred. Cross off an M, multiply by 2. Everything gets multiplied by 2, and then B squared, so take the square root. There's your answers. This is the velocity on slide A, this is the velocity on slide B. Here, all frictionless, so energy conserved, all equal heights. Which one reaches the ground with the fastest velocity, so meaning at the very end, the fastest velocity. Energy is going to be conserved, which means that I'm starting with all potential energy. They start with the exact same potential energy, so then I must end with the same kinetic since it's frictionless. And then they will all have the same speed then. So all start with the same potential. So we'll have the same kinetic at the end. So we'll have the same speed. Which one reaches the ground first? So they have the same speed, I'm going to say at the very end, because they do not have the same speed throughout. So if you look at slide A is very steep at the beginning. So A is steep initially. So it reaches that final speed earlier. So it has a faster average speed. Faster average speed. So reaches the bottom first. So this one, right? This one is going faster on average because it got to that faster speed first. This one, don't just say steeper, because this one's actually very steep. It's just very steep at the end, which means it gains that speed at the very end instead of being fast throughout. It was slow and then fast at the end. This one is fast and then gets a little bit faster at the end. Without manipulating equations, why does A have a faster velocity when it reaches the bottom? So energy is going to be conserved here. I'm starting with potential and going to kinetic in both cases. They actually start with the exact same amount of potential energy because I have mg2h and then I have 2mgh. Either way, this is the same amount of potential energy, which means they're going to go to the same kinetic. So both have the same potential at the top. So we'll have the same kinetic at the bottom. Now, normally having the same kinetic means the same speed, but that is not the case here because if you look at your equation for kinetic energy, 1/2 mv squared, if you have a different mass, that does not, that could be another reason, right? It's not just velocity, mass is also something kinetic energy depends on. So they actually have the same kinetic energy at the bottom. So if I have the same kinetic and I have more mass, that means less velocity. If I have the same kinetic and less mass, that means more velocity. Again, I can only say that because it has the exact same amount of kinetic energy. So same kinetic at the bottom. Part A has same kinetic with less mass. So that must mean it has a greater velocity because of this relationship right here. Now, if it didn't say manipulating equations, what I would have done is mgh equals 1/2 mv squared, and then 2gh equals velocity. So velocity at the bottom only depends on the height, so the more height will have a faster speed, but it said without manipulating equations, so I had to reason through it a different way. We've got a spring constant K attached to the wall, and the other is on a frictionless horizontal table, a distance h above the ground. A block M is placed and compressed a distance x, and then it is released. I want to know the velocity it's leaving the table with, so that would be like the velocity right here. So this is like my point A, and this is like my point B. I start with spring potential energy that's going to transfer into kinetic. Some people said, wait, that's a height h, that's fine. So at point A, energy at A equals energy at B. I definitely have spring. I also have some gravitational potential energy. That's equal to at B, where I have kinetic, and I still have the exact same spring potential energy, or sorry, gravitational. So this is 1/2 kx squared. This is a height of h, so mgh. 1/2 mv squared, and still the exact same height, mgh. So what will happen is I'm going to subtract this mgh over, and they're going to completely cancel out because it is something minus itself, that is 0. The other way to think about it is right here, right? I don't care what's happening after. Right now I'm just saying from this to this. I'm losing potential that goes into kinetic. This height above the ground is not going to affect the velocity that this comes out of the spring with, right? If this was on the ground, it would come off with the exact same velocity. If this was 25 meters high or higher, then it would come off with the same velocity. It's definitely going to affect like the second part, right? But this one, it's not changing height, so it shouldn't be. It doesn't matter. Find the velocity, multiply everything by 2, that cancels out the halves, divide the m over, and then finally take the square root. What can we do to make it travel a farther distance, d? So that's how far it travels, so coming off faster. What I could do to make it faster is a stiffer spring. That would be a bigger K. You could have a greater displacement. That's a bigger x. You could have less block mass. So those are the 3 things that I can do to make it come off of the table faster. But faster is not the only thing that would make it travel farther. You could also have it fall down farther, so you could also have a greater height. And if you're like, but that's not in the equation, that's true. I'm not saying a greater height has anything to do with the velocity. In fact, I know it doesn't, but it would have it travel in the air for a longer time while it's going that speed, which would make it go farther. Which would be more effective in increasing the distance, doubling k or doubling x? So the difference here is that this x has a squared attached to it within, so this is going to have more of an effect. So let's think about if I were to doubling k. So doubling k is going to mean 2 times the potential energy, which means 2 times the kinetic, which when you take the square root to get velocity is root 2 times the velocity. Now, if I double x, doubling x is 1/2 kx squared. That's going to be 4 times the potential energy, which means 4 times the kinetic, because it gets conserved, right, transferred, which is going to be 2 times the velocity. So if I put a 2 here, that's root 2 bigger for the velocity. If I put a 2 with the x, it gets squared, which is 4, and then square rooted, which is times 2. So this one is going to be a greater because this. Alright, 5, release from rest at point P, height h, frictionless, so energy is conserved. The velocity at B is VB, and I want to find the velocity right here. So I definitely need to have point A in there, right, equals energy at A, because that's what I'm looking for. At A, you've got both potential and kinetic. The height at point A is twice the radius, so mg 2 radiuses plus 1/2 mva squared. Looking for this velocity. Now, it's super important you pick the correct point to compare it to, because a lot of you want to use point P, which is mgh, but I was not given h, so do not use that. Now, I was given the velocity at B, so maybe compare it back to B. At point B, it's all kinetic energy, so that's 1/2 mvb squared. And then now I'm just rearranging to get VA by itself, cross off my m, multiply everything by 2, so this is VB squared. This gets multiplied by 2, so it's 4GR, plus gets multiplied by 2, crosses off, VA squared. Subtract over, and then take the square root. If the box was released from 2h, the velocity at point B would now be, so now I'm talking about h compared to B. So I'm going to say P and B. P is all potential, B is all kinetic. This is 1/2 mv squared. mgh, m doesn't matter, multiplied by 2gh. So the velocity at the bottom is just the square root of 2g height it was dropped from. If I release it from twice the height, it will be more velocity, right? So greater than VB, but that's not what I'm comparing. I'm saying is it more or less or equal to twice VB. So we have to look at our equation. If you put a 2 in front of the h, that's not twice as big because that's inside of a square root. It's actually times root 2 bigger. So your velocity would be root 2 bigger because of this relationship, right? It's inside of a square root. Root 2 is like 1.4 something, so this is times 1.4, which is definitely getting bigger, but it is not getting twice as big, so it is less than twice as big because your velocity is only root 2 times bigger from this relationship. From point B to point B, how does the mechanical energy of the Earth box system, so that is both potential and kinetic, that's the total energy. This is frictionless, so it will be conserved, so it will remain the same because the potential and kinetic energy is conserved because there's no work done. So that's not a guess. Right, frictionless, gravity is included, so that's not work done. Now, if I'm talking about just the box, so the box is kinetic energy only from point B to point P to point B, that would be increasing in kinetic energy. So this will increase because the box is gaining kinetic energy. Now here, we're saying, oh, that just comes from the Earth box potential, but I'm not including the Earth, so if I'm just looking at the box by itself, it looks like he's gaining energy. You could also say the force of gravity does work, positive work on the box. That's easier to just think about it as the kinetic energy, and we know that it's going to gain kinetic on its way down. Alright, we're initially at rest on an incline ramp. The base is a length d away. Released from rest, it slides down the ramp onto a horizontal surface, rough surface, until it stops right here. So this has friction, and then I'm going to stop right here. This is rest, released from rest, and not friction. Negligible friction between the ramp and the block. Here, this one has a coefficient of friction UB. Sketch and label the following quantities as a position between negative d and d. I don't need to like get a number for the vertical axis, but I have to use the same scale. So let's think about right here, from here to here, energy is conserved because it's frictionless. So the total amount of energy from, I'll just call this A to B right now, is going to be conserved. At A, it's starting at rest, so my kinetic energy, which is out, why am I calling it A? It's at negative D and 0. So at negative D, right, starting from rest, so that's going to be a kinetic energy of 0. And then as it is going down, it's definitely increasing kinetic energy, so I know it should be going up. So I'm just worried about this first section right now. So I'm going to have it starting at 0, and I know that I'm gaining kinetic energy as I go down, so I'm going to have it increase all the way to 0. And then we'll come back to what happens after 0. Now for gravitational potential energy, I start with some gravitational potential energy, and then it's going to decrease and be 0 at the end. So this one is going to be the exact opposite because energy is conserved. So I'm going to hit 1, 2, 3, 4, 5, 6 I. 1, 2, 3, 4, 5, 6 I. Has to be the exact same because energy was conserved here. So if I got 6 whatever units of kinetic, that means I must have lost 6 units of gravitational. So these should be the exact opposite because energy is going to be conserved, and I start with potential and it transfers to kinetic. Kinetic is 0, gets bigger, potential, have some, lose all of it. Now your potential energy from here to here, it has no height, so my potential energy is easy, it just stays at 0 for the rest of the time. Whereas my kinetic, I start with this. Now normally your kinetic would be conserved, right? It would just stay at this speed, but there's friction, and I know it's going to come to a stop at 4D. So at 4D, I know my velocity is going to be 0, so my kinetic energy should be 0. Now, I had to think about whether this is going to, I know it's going to decrease, right? It should be losing its kinetic as it goes. I had to think about whether it would do that linearly or not. So I thought about my work equation. Work equals FD. Work is the change in energy. In this case, it's just the change in the kinetic energy. So this is a linear relationship, right? There's no square to square root. So this will be a straight line between the change in kinetic and the distance traveled. So a straight line like this. First part is just the energy conserved, however much kinetic I gained come from the loss of potential, and then I didn't lose any potential, but or change any potential, but I am going to be losing kinetic due to the work done by friction. Alright, if we release this at a base of 2D, so same angle but 2D, that's going to be twice as high. I guess I'll draw a picture here. Same angle, but now twice the distance is going to go twice as high. A student is asked to predict whether the final horizontal position will be twice as far compared to when it was released from the original ramp. The student says that since the block will be released from a new height that is twice as high, we agree with that. The student reads, the block will have more energy and moving twice as fast when it reaches the base of the lamp, so it'll slide farther along the right surface before stopping at 8D, which is twice as far. So we have to decide what if that is correct. So I'm going to say for sure twice the height, so 2 times the height. 2 times the height is more potential energy at the start, and energy was conserved on the way down from the ramp, so that should be more kinetic energy at the bottom of the ramp. And more kinetic should take farther to stop, right? That makes sense. Now I just need to figure out, is it exactly twice as fast, and is it exactly twice the distance? So let's think about your kinetic energy. So instead of mgh going to 1/2 mv squared, which is 2gh, now I have square root of 2g2h. So twice the height is actually only 2 times the velocity. So that's going to be in our incorrect part. It is not twice the velocity at the bottom. It is only times root 2 faster. Okay? But it is definitely still more energy and faster, just not twice as fast. So let's go ahead and say that we do agree, which is correct. It is twice the height will give more energy of the block at the bottom, which is faster. So we agree with that, just not the twice as fast. And then we need to decide, does that mean it's going to go twice as far? Because I definitely agree going faster will take